to be a long one today because there's a lot to do. It's going to be one where you're going to need to stop it, make some notes, stop it, maybe answer a question. It's going to be very stop-start. It's going to take a while to get through. It's got quite a lot in it as well. But not only that, it's really crucial stuff. It's going to be a little bit of difficulty in what we do, really, I think, because it is kind of, well, firstly, it's probably new to you, but more importantly, it's got a bit of challenge in it, shall we say. So, its title's up there, Mass Spectroscopy Fragment Analysis. I'm going to remind you a little bit about mass spectroscopy before we go too far. Mass spectroscopy is a machine that you inject a sample into and it produces a set of results. Very much depends what you put in it, what sort of results you're looking for. We'll come to that in just a short while. A couple of things to remind you of. When you do mass spectroscopy, what you detect is a positive ion. So if you put in it bromine, for instance, you wouldn't detect bromine, you detect Br with a single plus. Or if it's split in half, you detect bromine with a plus. If you put in an organic molecule, you might get a bit of the organic molecule. Perhaps that. CH3, CH2, ether, but it would have to carry a plus. So whatever you do carries a plus. That's a fragment, that's derived from an element. So what we're focusing on today is the second part of what we do with mass spectroscopy. You, at this point, should be familiar with putting in an element and from the mass spectroscopy results being able to work out the relative atomic mass of that element. What we're doing this time is the second thing that mass spectroscopy is used for, which is fragmentation analysis or fragment analysis, or looking at what happens when you put in a large molecule and watching it fall apart. So here's a little sort of simple equation representing fragmentation. So the molecular ion, or the molecule as an ion, a lot of people write it as M+. Technically it's actually a free radical because it's got because you knocked an electron off of it, it's going to have an unpaired electron, so it's actually a free radical. And free radicals are not, on the whole, particularly stable, so what happens is it fragments. And they can fragment in a number of ways, and the more complex a molecule, the more ways it can fragment, and the more, therefore, lines in the mass spectrum you will get. But basically, it splits into, well, that looks like it splits into the same thing, so perhaps I should change that to be a different letter. There we are. So it splits into an N+, and I've said an N, which is not nitrogen, it's just the next letter in the alphabet, as a free radical. This is detected by the mass spectrometer. That is ignored by the mass spectrometer because the mass spectrometer only detects positive ions. So therefore, any free radical, no. It'll hang around. In truth, it may well get a second bang and split up again, and you get fragments again. But we kind of keep it simple at A-level. So A-level questions for mass spectrometry really come in just two guises. The two, I've mentioned them already. There's the relative atomic mass of elements. That's that where you work out the weighted mean and you end up with a reasonably accurate decimal placed atomic mass for an element. And you can turn those questions inside out, and you can have to work out what's the missing isotope that's in the data. Those are a bit more tricky, you've got to think about that. But that's not what today is about. And then there's this, what we're doing today, which is where you have the analysis of fragments, and those fragments go towards generating an identity for a molecule. This is going to be within a question, it's going to be part of the information of a question. But today we're just focusing on the mass spectroscopy part, but in reality of a question it will be mass spectroscopy information, and a load of other things, perhaps some reactions, perhaps some other types of spectroscopy like infrared information as well. So there'll be a whole collection of information, and it really is I ran out of space. It's a bit of a detective work. I'm going to do some detective work to find out what the substance is. Now, just want to make sure we've got the language of mass spectroscopy when we talk about fragment analysis sort of sorted. So this is all part of the, do you need to write it down? Probably. So the mass spectroscopy language. Molecular ion peak, M plus or M plus with a dot. I'm not going to write it down, but I'm going to tell you what it is. It is the whole molecule minus one electron. So the molecule stays intact. And that's really important because in the mass spectrum that comes out, that obvious, heaviest, they're called mass to charge ratios. Mass divided by the charge will be 1 in all A-level questions. So that is the one furthest to the right that is of decent size, but it's not the absolute furthest to the right. So we'll come to that really very soon. The base peak is the tallest peak out of all the ones that come out. It's usually given a 100% size and everything else is a percentage of that size. So the base peak is the tallest peak because it is the most commonly formed fragment during the process of running something through a mass spectroscopy machine. The M plus 1 peak is tiny. The M plus 1 peak is caused by, and there's a number of causes for it. It's caused by 1% of carbon being carbon 13 instead of 12. That makes it 1 heavier, M plus 1. Sometimes you get, at a much lower amount, what's called deuterium, which is hydrogen with a mass of 2. That's a proton and a neutron in the nucleus. And that raises it again by an extra 1. So you get an M plus 1 peak, which is always tiny and just past the molecular ion peak, but it will be visible but small, and the molecular ion peak will be obviously bigger. And it's quite easy to spot the last of the mass to charge peaks that you're interested in because it's followed by a little tiny one. And there's the language: molecular ion peak, base peak and M plus 1 peak. That's kind of the setup for it. I'm going to run quickly through how a mass spectrometer works, and I'll see you after the join. So just a little schematic of what goes on very simply in a mass spectrometer. You inject your substance in it. It needs to be vaporised because everything works in the gaseous state. And then you bombard it with fast moving electrons, so it gets a wallop from a fast moving electron. That ionises it. Now during the ionisation, that's when the fragmentation happens. So you get that. Like I said earlier in this video, it turns it into an ion and then it fragments. So that's the ionisation. Obviously that's critical to what we're doing today in terms of getting the things. They then get accelerated through the mass spectrometer. Now the reason it splits is there are 2 types of mass spectrometer. This is the old-fashioned type. When I did mass spectrometry, this is what we did. It was a great big machine with a curve of electromagnet. So you send it round the corner and it ends up at the detector, and the thing that is detected is mass over charge. The charge is usually +1, so therefore it just detects the mass of the fragment or molecule that or ion that you've detected. The slightly more modern ones are called time of flight, or TOF mass spectrometers. They don't go around a curve, they just go straight ahead. But because kinetic energy, and there's a relationship between mass and velocity, you can, from doing the calculation of the kinetic energy, you can work out the mass of the ion that was detected. That's just the time of flight. In the end, It's the results that come out of the detector that A-level questions are pretty much always going to be about. And if you notice, I changed the title, because what we're doing now is not doing the mass spectrometry, but we're going on to mass spectrometry, which is analysing what comes out as a result. So we're going to start with a fairly straightforward example, but we're going to not going to do the analysis. What we're actually going to do is we're going to look at the molecule and see what could happen on a simplistic level in a mass spectrometer. The reality is not that. The reality is it's much more complicated, but we're going to do a simplistic version. We're going to start with a first of our number of examples. Again, pausing and stopping and starting is going to be really good. I'm going to clean the board up and get it ready for the first example, and I'll see you very shortly. So here we are with example 1, which I should have written on there. Example 1. This is propan-1-ol. One of the series of alcohols. Formula mass is 60. So you will get a peak at a mass to charge ratio of 60 for the molecular ion. So that's not fragment, that's the entire molecule staying intact. Most of the time, more fragments are formed than the molecule stays intact. The molecule tends to be unstable when it's a free radical, so you get fragments. So this is the sorts of fragmentation you can do. So we can chop it there. So that would be number 2, I've already done number 1. So you could chop the hydrogen off. So you are then left with CH3, CH2, CH2O plus, or okay, that has a mass of, well, you've lost 1 hydrogen, so it must be 59. You can then chop it there, removing the OH. Now that leaves you with a propyl group, but as a positive ion, CH3, CH2, CH2 plus. So what you've now lost is O and H. O and H add up to 17. So you're 43. So you will detect and have therefore a vertical line at 60, at 59. That one will be, tends to be less in size than that one, although sometimes it's bigger than the molecular ion peak. It's all a bit random, I think. This one, very much in evidence at 43. Then you can slice it at that position there. I've called that number 4. So there. The other part, this CH2OH, will be the free radical and not detected. Wait. So this is, well, you can just say, oh, that's 29, because you could just add that up. 15 and 14 is 29. So that's another line that you will see. Now if you did this number 4 and you did the split the opposite way, so that the CH3, CH2 became the free radical and didn't go through the mass spectrometer, this end will be the positive ion. So it wouldn't be the same molecule, it would be the splitting of a different set of molecules, because there are crazy large numbers get injected in, even in a small sample. So we would have CH2OH there, plus as the other alternative way of doing split number 4. So that is also CH3O, that's 15 and 16, that's 31. So 31 taken away from 60 is 29, so there's always a reference back to where you started. Now you could also, number 5 there, lop off the methyl on the end, and you could do that the same thing. You could do CH3 plus, and that's 15. Tends not to come up very large as a peak in mass spectrometry when it's 15. Not entirely sure why, but it doesn't. And then that leaves you with, if you split this the other way and the CH3 dot was the free radical and then this became the positive ion, you get that. Now that also adds up as that. Basically, split it any way you can. Take off a hydrogen. It doesn't matter which hydrogen you take off, the molecular ion will have the same mass. I say that this one is the weaker of all the bonds because it's polarised, and therefore it's easy to nop the hydrogen, block the hydrogen, nop and block, new made up words. Right, so you can basically split it wherever you like. That also means missing from that is OH plus at 17, tends not to be a particularly visible peak, that. So that's the companion one to doing this. And you never detect hydrogen plus, it's just too small. So, therefore, 60, 59, 43, 29, 31, 15 potentially, 17 potentially, and 57 definitely. So that gives you the origin of a number of peaks that you could get from Propane 1O. The reality, like I hinted at before the join, is that it's actually much more complicated. In a mass spectrometer you then get refragments, rearrangements, and you get a whole load more than these. But A-level doesn't get involved in all of that. So that does mean that A-level spectra tend to have obvious big peaks that you can see and a whole load of chattering small peaks that we ignore much of the time. I need to move on to example 2. I'll see you in a moment. So here we are with the second example. Same formula mass, 60, different compound, ethanoic acid, carboxylic acid, vinegar. Some the same, some different, as you will see. So molecular ion peak, CH3COOH, with a plus charge on it, will be at a mass of 60. Break it at 0.2, lose the hydrogen, we will get CH3COO plus at 59. Break it at 0.3, losing the OH, where you could have it at 17, but the reality is these ones tend to be quite small. Hard to see that one. This one you can often just about catch. You can just about see the 15 in a minute. So break it at 0.3, we get CH3CO. Now OH is 17, so it will be 17 off the 60, which is 43. And then if we break it at 0.4, we get the CH3, which is the 15, which will be quite small, and we get COOH carrying a plus charge, which is 15 off of the 60, which is 45. Or you can just add it up as CO2, which is 44, and an extra hydrogen is 45. But they all carry a plus charge. When they ask you what could cause this mass to charge peak in a mass to charge ratio peak in a mass spectrum, if you don't put the charge on, the plus, you won't get the mark. You know, it's as straightforward as if you don't remember that you don't get the plus ions going through the mass spectrometer, you're not going to get the mark. So always remember that. Write that down. It's very important. People forget that. Or somebody lose all their marks because of that. Right, so there's the breakdown of breaking up ethanoic acid. Like I said, the reality is you get a whole load of other chatter, but these numbers are going to be the ones that you're looking for. You're looking for a molecular ion peak, and don't forget there'll be a little tiny peak at 61 for the N+1. There'll be one at 59, there'll be one at 43, there'll be another one at 45, and you'll probably be able to detect one at 15. Unlikely to see too much of one at 17, but you might see a little bit, and so therefore you get that. That is fairly similar, but not identical to the previous one. And that's the power of mass spectrometry, is that when you analyse it, you can often work out what the mass spectrum was related to. Certainly when you've got some additional information, it's very clear. So that's example 2. In example 3, I want you to have a go, but I need to put it on the board first, so we're just going to have a little break, and then I'll see you after the break. So, example 3. This time I want you to have a go. Just let me explain what I want you to do. So, ethanol, CH3CH2OH, formula mass, you'll need that. What I want you to do is pause me in a moment and try to predict the obvious peaks that you're going to get in the mass spectrum of ethanol. I will go through what you get, but part of the process of getting the most out of this video is for you to pause and do something yourself and be challenged to do it, rather than just let the video run and go, oh, that was the answer. I'd rather you stopped it, had the challenge, and probably do reasonably well at the first attempt, I hope. So we're going to pause it, and I'll see you in a moment. So, I wonder what you got. Here's the obvious predicted peaks. Molecular ion peak, 46. Take off the hydrogen on the end, 45. Take off the OH, CH3CH2 plus an ethyl positive. CH2OH plus. 17 OH plus, but I put it in brackets because it's unlikely to be really obvious. 15 CH3 plus, and of course there will be a small N+1 peak at 47. So that means there were 1, 2, 3, 4, 5, 6, 7 to identify. How many did you get? Well, hopefully most. You did quite well if you got most of them for your first attempt. So we're going to have another go with another chemical. So you need to get the board ready for that. I'll see you in a moment. So here we are with example 4, hexane, CH3CH2, CH2, 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 CH3, C6H14. So, again, to get the most out of this, I want you to pause and I want you to predict. I'll see you after you've paused and predicted. So, hope you've had a go. Here we are with some breakdowns. Formula mass is 86, so the molecular ion peak will be at 86. Lose one hydrogen, you get a peak at 85, it's quite small. N+1 peak, noticeably small, at 87. And then we do the pinching off or chopping off parts of the molecule. So take off a CH3, C5H11 plus is left, that's 71. I'm disappointed with the size of that in the actual mass spectrum when you look at the hexane, but nevertheless it is there. And chopping it the alternative way and getting the methyl to be the plus gives you a peak at 15. Do the same chopping off CH3CH2 ethyl. You'll get a 29 if the ethyl comes off as a positive, and you'll get C4H9 plus, a butyl, if that comes off as the plus, and that's 57. And if you basically split the molecule in half, you get C3H7. This is going to be a particularly obvious peak because it's, it's formed either way that you split it. Propyl, 43. So you get 87, 86, 85, 71, 57, 43, 29 and 15. How many is that? Oh, I didn't count as I was going along. 1, 2, 3, 4, 5, 6, 7, 8. How many out of those 8 did you get? If you got all 8, little cheer. Woo! Oh, sorry. Right. Then, I have an observation. Have you noticed that we keep seeing the same numbers? You haven't? What have you been doing? 15, 29, 31, 43, 45. These are numbers that come up all the time. There's one other number which we're not going to touch on in this video, which is 77. Although I will mention it in just a moment. But it's also this kind of thing here. This is what I don't know if this is the official language for it, but I call it subtractive analysis, where you go 86 to 71. Now of course this is doing the thing in the other way. This is, here's the mass spectrum. What causes a peak at 71? Well, what's the difference between 86 and 71? It's 15. That's losing a CH3. That kind of analysis is actually more like what you're going to have to do. So we're going to move towards that. But we can take a little pause whilst I get ready for example 5. See you in a moment. Before we do example 5, the magic numbers. They're not called the magic numbers. I call them the magic numbers so you stand a chance of remembering them. But they're actually just called mass difference numbers. So what I'm talking about is not fragment. I mean, you can have these fragments, but it's the power in mass spectroscopy is not about going, oh, that's what these fragments represent. It's actually, these are when the differences have dropped by 15 or 17 or 29. So when you look at two peaks, the molecular ion peak and another peak, the difference between them, if it's one of these numbers, it indicates it's quite likely, well, there are other ways to do it, but quite likely to have been one of these pieces of molecule chopped away. So if you lose 15, so if the gap between two peaks is 15, you've lost a methyl, 17 OH. You must have picked that up already from the examples that we've had so far. C2H5, really important that, because if you don't have CH3, CH2 in the molecule, you can't drop a 29 between two peaks. So it does tell you that if there's a drop of 29, you've got CH3, CH2 in the molecule, although there are other ways of getting 29. But if it's not there, then with a gap, the structure can't have CH3, CH2 in it. 31 is lopping off a alcohol at the end of a molecule. So CH2OH is a terminal, a primary alcohol popping off. 43, either, and this is where it gets a little bit annoying because they're both the same, you're chopping off propyl, which means you've got 3 carbons in a chain that you can chop off, or you're chopping off this, sometimes called acylium or acylium, I can write it but I can't say it. CH3CO, so it's like part of a group where there's a carbonyl in it and something else, and that could go on to join to a number of other things, and it appears in a number of guises in organic chemistry. 45 is indicative of a carboxylic acid group being snipped away, and this is the 77, which I'm not going to do in this video because a lot of people haven't done benzene chemistry at this point. This is chopping off a benzene group out of a molecule, so this will be attached to something else in the molecule, and so you've chopped off C6H5 because there's a hydrogen in each of those positions and you've broken it at the point where it's joined to something else. So 77 is when you chop out a benzene ring. But benzene rings are prone to have other things attached to them as well, so it's not that clear that it's always going to be 77. Right. Don't call them magic numbers when you answer questions, because that's wrong. We mustn't call them that. They're just mass differences. Right, see you in a moment for example 5. So something slightly different before we go into drawing spectra and trying to work out what's going on is bromomethane, CH3Br. I want you to do a little bit of predicting bearing in mind that bromine is pretty much a 50-50 mix of 79 and 81 in terms of isotopes. So I want you to do a prediction of that, and wherever bromine appears in your fragment, say something about the height of that fragment compared to the other fragment that comes with it, because the fragments come in pairs when there's bromine, because there's one when there's 79, one when there's 81. Right, time for you to pause and predict in order to get the best out of today's video. See you in a moment. So, a little bit to think about, but the fragmenting is really straightforward. So 94 and 96 are going to be the two molecular iron peaks, and they'll be equal height because the bromine will be one of either 81 or 79. So it'll be a 96 and 94. There'll be an M+1 peak for each one of those at 95 and 97, really small. Then you can take a hydrogen off and you'll get CH2Br, and that'll be at 93 and 95. And that won't give you an additional peak because the 95s will be the same regardless of what the origin of them is. In fact, that will be so small that it won't make any noticeable difference to the 95. You can break off the bromine, and then that leaves you with a CH3+, or you can break off the bromine as a Br+, and that will give you a 79 and an 81, and those will be equal height. So whenever there's a bromine involved, there'll be a pair of peaks at equal height. That means there's 8 peaks in there, I think, or is it 7? 1, 2, 3, 4, 5, 6, 7, 8. 8. There we are. Right. Okay. Now we're ready to do the reverse, which is much more likely the sort of thing you're going to see. You're much more likely to get a mass spectrum and get told to do something with what you see. So we're going to pause. I'm going to put the mass spectrum up, and we'll go from there. See you in a moment. So here we are with example 6. Time for some detective work. So what you're going to be doing is piecing together the evidence. That's how these questions are usually going to be. We've been joined by a fly. And it's a very simple mass spectrum. I've put the numbers on so that we have no conflict about what mass to charge ratio we're talking about. You often have to read them off a scale along the bottom, and the scale will be in 5s. Hopefully there'll be some tick marks, but if they're not, got to make an estimate of what it is. So 58, that's the molecular iron peak. Tells you that the formula mass comes to 58 with whatever it is. So MR is going to be 58. There's a little tiny 59, that's the M+1 peak. There's a 57, but it's not very big, where we've locked off a hydrogen, but we don't know what the formula is in order to write that at the moment. So what do? We go 58 to 43. What do? We take off 15. That tells you that you can lose CH3 out of the structure fairly straightforwardly. So 15 loss produces 43. This is that subtractive analysis. And then, this is quite important, you can't see a 29. So if you take 29 off of 58, you get 29, so it doesn't matter what you do. What's left is 29, and what is removed is 29, but you can't see a 29 in either guise. So there's no presence of C2H5. Now that does mean that you're somewhat focused on the fact that, okay, we can't have a line of carbons. Now when it comes to 43, going back to those numbers, 43 can be caused by one or two things. It could be caused by the propyl C3H7, but if you've got propyl, you could nip off 2 of the carbons and get a 29, and it's not there. So that isn't the 43, because it would have caused you to have a 29, and there is no 29. There'll be some little chatter along there, all sorts of things, but nothing of any significance of 29. So that means that is likely to be present in the molecule. Now when you do that, and you've got a CH3 joined onto it, kind of leaves you with only one choice, which is that. Propane. So you chop off a CH3 and you get CH3CO. It's quite a stable ion, so it'll be there at a large, that's why this is large, because if an ion is stable enough to exist in the mass spectrometer for enough time to fly down it, it will be a big peak. So therefore we have identified by going in two things really. The drop of 15 we can chop off a methyl. The fact you can't drop off 29 means that there is no propyl. Therefore we're down to propanone, the ketone, the smallest ketone. That's the answer. That's example 6. Time for example 7. So here we are, example 7. Now the spectrum is not on the board, it's going to come up, should be there by now. Yeah. It's also, you've got it on a piece of paper if you've taken the file that comes with this and printed that out, because there's a lot more in this. This is a real mass spectrum. As you can see, it's taken from a web source. The substance that it is has the empirical formula C3H6O. Now when you do these questions you always get a whole load of additional information. You don't just get a mass spectrum, you might get some infrared information, or you might get some chemical reactions that it does. So when you look at that, what I want you to do is identify the mass to charge ratios of the obvious peaks. I'm going to ask you to pause, and I'm going to ask you to do identifying the mass to charge ratios of the tall peaks that are of importance, or any other peaks that you think are important. See if you match what I do whilst you're doing it. I'm going to put them on the board. See you in a moment. Important peaks that you should have picked up are in a box. 116 molecular ion peak. Now that, when you look at the formula mass of that, when you double that, it's 116. So that tells you that the molecular formula is then doesn't tell you massively what's going on at that point, but that's 116. Then you've got a peak at 87. 87 is 29 down from 116. You can lose C2H5, importantly. So that tells you that you get 2 carbons in a line minimum in the chain. You can knock off 75. Sorry, you can have a peak at 75, which is a knockoff of 41, so I did that wrong way around. You get a peak at 57, where 59 is lost. You get a peak at 43, where 73 is lost. Now 43 is going to be one of those two things. Yeah. But it's going to be this one, because that's going to be, it's going to mean there's going to be 15, and 15 is, that's going to produce enough 15 that you would see it. But when you look at the spectra, 15 is not obvious. So it's likely to be this one. You get a peak at 29, which is the ethyl coming off. Now what you then go is, how do I get, because this is the important one, what if I take off that from that, I get that. There's the propane. Oh, the traffic has gone. There's the propane and there's CO2. This is actually going to be an ester. And there's that joined to that. So there, this side of that is the 87. There's the 29. It turns out it's propyl propanoate. Now it is actually possible to have other structures that fit with just those ones identified. It is unlikely to be a branched version of this where you've got because if you had that arranged in that structure you would get 15s appearing quite obviously in the mass spectrum when they're not there. So it's likely to be just a straight CH2, CH2, CH3. And that's the structure. Not necessarily would you get a question where that is all the information you get. You would get probably more information. There's a number of reactions you do to hydrolyse an ester and get products that you would identify and so forth. It's likely to be within further information, but I don't want to make it unwieldy on a video. Got one more example to go, and then you're up to the do it some yourself on the question sheet. I'll see you for the last example. So here we are with the last example. A bit more detective work. Additional piece of information. There's an infrared absorption at 1750 wave numbers. Surely by now you should have done the infrared video. Here's the peaks that crop up on the simplified mass spectrum. Now at A level sometimes you get the proper mass spectra and you have to pull out of them the important peaks. They will be clear that they are the most important peaks because they'll be obviously tall. Or you sometimes get the simplified mass spectra where they've cut out all the chatter of other things going on to make it less confusing. Yeah, it very much depends on what the board are thinking of at the time. Those are the important peaks. I would like you to have a go at thinking, what could they be caused by? In the context that you've got 1750, you might not have a quick look at a data booklet and work out what that infrared absorption leads you towards. And I will see you when after your deliberations about your deductions and detective work. See you shortly. Now this is disgracefully tricky. The 1750 absorption indicates ester or acid anhydride. I hope you saw that in the data booklet. The smallest acid anhydride, and this is the tricky bit because if you don't know what they are it's a bit difficult, has a formula mass of 74, that's methanoic anhydride. So it can't be this substance because the molecular mass is 60. So that means it has to, by default, be an ester. 61 is the N+1 peak, don't really matter. 59 is you've dropped a hydrogen. We know what 59, the Y1 under would be that. It's tricky because 45 leads you to be going carboxylic acid, but it doesn't always mean carboxylic acid. It's not that because we've said it's an ester, and an ester won't have that functional group. It'll have something else instead of the hydrogen there. So it is, we are saying HCO2, but we are saying the arrangement is not that. The arrangement is actually going to be that. That's the methanoate part of the ester. And then 31. Now in the previous things we've said it's CH2OH+, but again that's not a functional group you find in an ester, and we've said from the infrared it has to be an ester. But if you rearrange that you get CH3O, methyl ester. So 29. Now you would go, oh, 29, he told us that was C2H5. Yeah. But if you had an ethyl ester, it would be higher than 60 as the formula mass. So there must be another way of getting 29. 15 on the other hand, CH3 plus, definitely. Now when you look at the structure that I've got here, this is methyl methanoate. There's the 15, CH3 plus would come off. That is this structure here. What's the formula mass of that? 45. Yeah. So what happens if you chop it there? If you chop it there, there's the 31. What's that? That is 29. That's an alternative for 29. It's much less common because it is actually derived from a methanoate ester, and you know, there are lots of other esters you could have. So the actual substance, just for completion's sake, now the whole point of this example is to show you that sometimes what you think is obvious and what you think it will be cannot be when you go through the full deductive process. In this case it's driven by the 60, it stops you having ethyl, it stops you having acid anhydride. Right, I told you it was a long video, feels like it's been a long video making all the clips. Now, there are some additional questions for you to have a go at, very much well worth having a go. It's going to be a long job. Always come back to the video, review it again, realise that your notes weren't good enough, make some more notes, extend your notes, look in your textbook, see what you think. Good luck with the questions, the answers will be there as well. I'll see you for the next video when we do a further type of spectroscopy. Thank you for watching. See you soon.